Welcome back to Applied Algebra and Trigonometry. Today we're going to be looking at the polar form of a complex number. To explain what polar form means, let's first look at an example of a complex number that's written in rectangular form and is graphed in rectangular form. Now, looking at this graph, we could complete a reference triangle here, right? And if we do that, we see that our x component, or in this case our real component, is 3, and our imaginary component is 4. But let's look a little closer. Remember what we were doing with our vectors when we were breaking things into components? Instead of talking about that hypotenuse as 3 plus 4j or something else, we gave it the symbol of r, because we could be talking about it as the radius of a circle with a center at the origin and a radius, the length of that, what is now an arrow, the length of that side. And we know that the x component of this triangle could be found by multiplying r by the cosine of this angle, theta. Likewise, we could use r sine theta to get the side opposite this angle. We have a value for the real component, 3. We have a value for the imaginary component, the coefficient there, 4. We don't have a value for the hypotenuse. We have this imaginary, or complex number rather, but if one side of a right triangle is equal to 3 and the other side of a right triangle is equal to 4, what is the hypotenuse of the right triangle equal to? The answer to that is 5. For this specific example, our r value is 5. But what is theta? Well, we can figure that out because we have been given, or I gave it to you in 3 plus 4j, I gave you the y component of that triangle, or the j component in this case, and I gave you the real component, which is along what's usually the x-axis. Anyways, we can apply tangent to this. We can take the tangent of theta to be 4 divided by 3, right? But we're trying to find theta. Let's take the inverse tangent of both sides. When I punch that into my calculator, I get 53.1 degrees. I'm going to do this in degrees first. And now that we have all of that information, by the way, theta is a reference angle, but we're working in the first quadrant, so we can say that the reference angle is equal to theta. So we're good. We started with 3 plus 4j. We now know that 3 is equal to the real component down here. In fact, at this place, I should probably write 5 cosine of 53.1 degrees. So that's what 3 is equal to. It's equal to 5 times the cosine of 53.1 degrees. We're adding to that our value for the imaginary component, which, if we look at this, is equal to 5 times the sine of 53.1 degrees. So we can put that in here. So we have our value for 3, and we have our value for 4, but we still have a j that needs to go onto the end. Now, we also have a common factor in both the real component and the imaginary component. That common factor is 5. So this can be rewritten yet again as 5 times the cosine of 53.1 degrees plus the sine of 53.1 degrees j. Take a look at that. Is j part of what we're evaluating with the sine, or is it multiplied by the sine of 53.1? It is the latter, so we need another rewrite. This becomes 5 times the cosine of 53.1 degrees plus j sine of 53.1 degrees. What we're saying is 3 plus 4j is equivalent to 5 times the cosine of 53.1 degrees plus j sine of 53.1 degrees. So to put this in a purely symbolic format, a complex number a plus bj is equal to whatever the hypotenuse of the reference triangle is, or you can also think of it as the radius of the circle, times the cosine of theta plus j times the sine of theta. And this is what we're going to use. The past is prologue. The past, what we've just done, is the derivation of this formula. So let's take this formula and let's apply it. Okay, vocabulary review. This is the what form. The answer is rectangular. All right. And what might these be called? Theta, your angle, which angle? Okay, these are called the argument, or rather, whatever that angle is the argument. And then we have r. We don't call it the radius. No, that would be too simple. We call it the absolute value. Okay, that's a familiar term. What does that tell you about whether it's going to be positive or negative? Yep, always positive. It's also called, sometimes, the modulus. Okay, so either one of those is fine. Now there's just one problem with this, and boy, that's a mouthful and a lot to write at the same time. Since we're always going to have the cosine of some angle plus j times the sine of that same angle, is there an easier way to write this? Well, yes. And that easier way to write it is r with this oversized angle sign, theta. Thus we have simplified the polar form of a complex number to the modulus, big angle sign, and then the argument. So hang on a moment. Let's make a list of all the formulas we've talked about and that we're going to need. Looking at our first triangle and remembering our Pythagorean theorem, we can say a squared plus b squared equals r squared. Remembering our trigonometry and comparing the upper triangle to the lower triangle in the pictures I drew over there, we have a equal to r cosine theta, b equal to r sine theta, and the tangent of theta equals b over a, using the absolute value of that ratio, of course. That fact leads you to the formula that the reference angle is equal to the inverse tangent of b over a. By combining these formulas, we now have different ways to express a complex number graphically and symbolically before we graph it. We have a rectangular form, a plus bj. We have a polar form, r times the quantity, the cosine of theta, plus j sine of theta. Okay? And then we have a simplified form of that, which is r big angle sine theta. Knowing all of this, Let's do another example. Let's call this example 2. And we'll say you're given this expression, which isn't really in the correct form. So the first thing you would need to do is to put it into the correct rectangular form. Yeah, that looks like the rectangular form of a complex number. Now, let's convert this to our polar form. So how would we do that? Well, we have to figure out where this is first. So let's draw a coordinate axis. And we're going to go 5 in the negative real direction. And then we're going to go 12 in the positive j, or imaginary direction. So, very quickly, here is the triangle with which we are working. And if you remember that this is a special triangle or use the Pythagorean formula or theorem, you can figure out that the hypotenuse, which is always positive, is 13. But then we need to find this reference angle. So since this isn't a usual angle that we memorize, let's refer to our calculator. I should note that I had to change my calculator from radians to degrees to get this correct. So our reference angle equals 67.4 degrees, but what is our actual value for theta? Okay, standard angle goes from 0 and never reaches pi, or excuse me, we're doing degrees, so 180 degrees. In fact, it's 67.4 degrees less than 180. So theta actually equals here 180 degrees minus 67.4 degrees. And that gives us 112.6 degrees. Now we can do our conversion. Negative 5 plus 12j is equivalent to 13, the cosine of 112.6 degrees plus j times the sine of 112.6 degrees. And we could further express that as 13 big angle sine 112.6 degrees. Which form you use depends upon the application for which you are using it, or which one your professor tells you to use. So let's work in the other direction now. The voltage of a generator is represented, or a certain generator is represented by this 3.03 big angle sine 339.5 degrees, and this is all in kilovolts. Your instructions are to graph this and then express it in rectangular form. So we need a Cartesian axis. 339 degrees will put us somewhere around here, and we can express our complex number then as having a radius of 3.03. Okay, so we have it graphed, but let's change it into rectangular form. In order to convert our original form of this complex number to a rectangular form, I highly suggest you go through the intermediate step of rewriting it using you could call it the expanded polar form. Cosine of 339.5 degrees plus j times the sine of 339.5 degrees. Let's look at our components. Take note, please, that the hypotenuse, or the r value, 3.03, when distributed, is multiplied by the cosine of the angle, which is what we have here, our real component. And then also, it is distributed to be multiplied by the sine of 339.5 degrees, which is our imaginary component. So this is equal to 3.03 times the cosine of 339.5 degrees plus 3.03j times the sine of 339.5 degrees. And when we evaluate those expressions, we get 2.84 plus, actually, it's going to be a minus because it's minus 1.06j. So we're just going to erase this and combine it by adding a negative being the same as a subtraction. So there it is in rectangular format. Here's where we started, and then this is where we wound up. And that is in kilovolts. And now let's talk about some special complex numbers. Here are the complex numbers graphically, and I have begun my chart with the rectangular form of the first one, the red one, that is 5. In polar coordinates, that would be 5 angle sine 0 degrees. Okay. Next up, we have 3j. What would that be? In polar coordinates, that would be 3 angle sine 90 degrees. Our -2, which is the yellow arrow in the negative direction on the real axis, would be -2, 180 degrees. And finally, in the -j direction, we have -4j. And in polar form, that would be -270 degrees. Where'd the j go? Well, if you remember, this is short for this whole thing. So it's within there. It's just not visible. That concludes our discussion of the polar form of complex numbers. I will see you in Collaborate.